Hello everyone, let's take a look at our next problem. A spring has natural length of 20 centimeters. Compare the work W1 done in stretching the spring from 20 to 30 with the work W2 done in stretching it from 30 to 40. How are W1 and W2 related? Okay, so I'm going to draw a diagram first of all of what's going on here. So this is my spring. It has a natural length of L. Natural length of what I will call L. It's given in the problem as being 20 centimeters. And we're asked, in stretching it from 20 to 30, and then further stretching it from 30 out to 40, how are the two types of work related? So I'm trying to remember the way energy works for springs. If I remember Hooke's law correctly, force is equal to K times X. I'm not worried about directions or signs of things at the moment, but X is the distance from natural length. Okay, so I'm going to set up a coordinate system here. I'm going to say that when the spring is sitting at its natural length, our x-axis is going to go this way, and this point here is x equals 0. And so the 2 points that we're concerned with are when x is equal to 10 and when x is equal to 20, because that'll correspond to moving the spring from a length of 20 to 30 and then again from 30 up to 40. So this is the force which the spring is exerting on this point, depending on how far stretched it is away from x equals 0. I suppose if we really want, if we want directions to be consistent here, then I should have a negative sign in front of k. Now to figure out the amount of work done in stretching the spring from x equals 0 out to x equals 10, well, the force is changing as this point of the spring is being dragged along. So what we're going to have to do is integrate this force from x equals 0 out to 10. So W1, the first quantity we're concerned with, is an integral from 0 to L over 2 of f dx. I suppose it's actually negative f dx, because the way I've written this f is the force that the spring exerts on this point, but the work that we're doing is in the other direction of that, so I'll put a negative sign here. So from 0 to L over 2 of kx dx. And just doing this integral and evaluating at the two endpoints, I have k times L squared over 8. So that's W1. And W2 is going to be the same integral, but I'm starting at L over 2 and integrating out to L. Again, it's going to be the same quantity kx dx, which is just going to be kx squared over 2, evaluated at the two endpoints, L over 2 and L. So now I have k L squared over 2 minus k L squared over 8, which is what? Multiply by 4 minus 1 is, so this is 3k L squared over 8. Okay, so W1 is kl squared over 8, and W2 is 3 times larger. This should, it makes intuitive sense that W2 is greater than W1. When you pull on a spring, when you pull on some kind of spring yourself, stretching it by some distance from its rest point is easy, but then stretching it The same distance beyond that point is significantly more difficult. And in this case, it shows that the factor between them is a factor of 3 when the total length stretched overall doubles the length of the spring. Okay, so the relationship we have here is that W2 divided by W1 is 3. So good little problem. Nice to set up a coordinate system as usual, so that conducting the integrals becomes pretty straightforward.